Hello everyone again, and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video, we're going to be exploring something quite interesting. Once you're given a particular amine or a particular form of nitrogen-based hydrocarbon or organic compound, and you're trying to incorporate it into an aromatic ring, you might be asking yourself, how is this established when you're doing it in a really fast process, which means in the presence of a particular catalyst? Usually we use palladium in this particular part, and this question actually led to some interesting research that is really magnificent based on palladium catalysis. And in this video here, which is a part one, we'll be looking at amination of aromatic rings, and this is going to be leading into one of the key themes that we need to talk about based on our specific goal, which is to use palladium to help form carbon heteroatom bonds. And you'll ask yourself, why heteroatoms? This is really crucial because you're improving the diversity of hydrocarbons and how this connects really well to various organic systems. It's truly magnificent seeing how you can recreate it using various catalysts, like for example palladium here. So in this part here we have carbon, which is part of the aromatic ring and is going to be incorporated into a specific heteroatom. And this heteroatom, we don't know where it is, but our goal here is to use palladium here. Once it comes in as palladium 0, transforms into palladium 2, and then creates the sigma bond, and then converts back to palladium 0 for another cycle. It is able to incorporate various forms. Maybe in this case we might be focusing on a type of heteroatom, which is sulfur or oxygen, or maybe most likely of focus for this particular video will be nitrogen. So nitrogen will be our main focus indeed for this particular reaction, where we're going to be forming a carbon nitrogen bond or an aromatic amine bond created with the presence of palladium right here. So this focus here now leads us to what is the approach to accomplish this particular task. And so our approach here is to first look at the following type of reaction, which is actually proposed by Buchwald and Hartwig. And this Buchwald and Hartwig reaction comes in various forms. One is we're going to look at the end game of this particular reaction, and next is to look at a reaction specific example and then apply this particular reaction mechanism to this particular example. And finally here is to look at alternatives, either being the base or and looking at the specific ligands, and this will be crucial for our specific analysis of this Buchwald-Hartwig reaction. So what is our end game, which is the main focus in here? And our end game here is going to be focusing on the main theme, which is that palladium can be used to promote nucleophilic substitution at aromatic vinylic center. What does that mean? When you're given a reaction where you have an amine and this is going to be incorporated into an aromatic ring in the presence of palladium, we need to keep in mind that we need a particular halide that will be a good leaving group on this particular aromatic ring. Therefore, once this good leaving group is actually cleaved off during this catalysis process, we can introduce our specific nitrogen, which is a form of a nucleophilic substitution process that is going to be done in this particular region right here. So this amine is really going to be introduced here. But what type of amine are we talking about? Yes, it could be a primary, secondary amine, depending on what type of structure that you're focusing on. So we are here going to be diving really deep into a specific example, and this specific example is going to be looking at this particular form of aromatic ring that has a form of halide, in this case iodide, and this will be subject to a form of an amine. This in this case is a secondary amine, and therefore this will be done in the presence of our catalyst, which is palladium dibar, and this is done in totaling phosphine, and this is going to be done in the presence of our base. In this case, it's going to be sodium third butyl oxide, and then we have a dioxane, and this is done at 65 to 100 degrees Celsius. Quite a hot temperature to keep in mind, and this leads to the formation of our aromatic ring attached to the specific amine in a process called amination of our aromatic ring. And this is our key goal to keep in mind. Our goal is to be able to get this out and get this hydrogen out, and then form a bond between the nitrogen and the specific carbon right here. So keep this in mind when it comes into this particular reaction mechanism, and our reaction mechanism will be the key step to follow, where we need to be able to then look at how to use this space. I'm just kidding, we're not going to use this space, we're going to need more space to make this actually come into fruition. And so this is where we begin in this particular reaction, where we are going to start off with the mechanism. And so the mechanism is as follows. First, we need to look at a particular process where we need to begin with our specific palladium as the catalyst, and this catalyst will be starting from palladium 0, and in the presence of our specific aromatic halide is going to actually perform oxidative insertion of our palladium 0 into our allyl halogen bond. Therefore, this is going to be created as a result of this particular bond forming a bond with the palladium, and therefore palladium forms a bond with the carbon. Therefore, this results in our particular oxidative insertion that creates our specific palladium 2, and therefore our next step is to be able to focus on our palladium 2 complex that adds our amine. And so our amine comes in contact in here, where our nitrogen region, which has a lone pair, is going to be fusing or creating a bond with the palladium center, and as a result of that, we're able to form our specific intermediate complex, where our nitrogen is bonded to our palladium, creating our positive charge on the nitrogen. And therefore this leads to our next step, where we need to keep in mind that, hey, since we have this created, we need to change our nitrogen into a specific neutral atom. And so therefore, to make the nitrogen to be neutral, we need to deprotonate our specific nitrogen. Therefore, we need to introduce our base to eliminate not only the hydrogen here, but also our specific iodides. Therefore, to accomplish this, our specific sodium third butyl oxide is going to dissociate into first our sodium ion, and the other side we have our anion, where our oxygen lone pairs is going to deprotonate in here our specific nitrogen, therefore picking up our hydrogen. This hydrogen nitrogen bond becomes a lone pair on the nitrogen. Therefore this triggers this complex to let our iodide to become a good leaving group. Therefore our iodide leaves, and this forms our side products, and as a result of that, we recreate or generate our specific intermediate complex, and this intermediate complex is now ready for our final step, which is called the reductive elimination. Therefore our reductive elimination leads to the formation of our allyl nitrogen bond. So therefore, as a result of that, once our lone pair becomes a specific bonding pair between the nitrogen and this particular carbon, this bonding pair between the carbon and the palladium forms a lone pair with the palladium, and finally our palladium with the nitrogen bond cleaves to become a lone pair on the nitrogen. Therefore this leads to our establishment of our reductive elimination product, where one side we have our specific allyl nitrogen bond created, and on the other side here we regenerate our palladium 0 from our palladium 2 complex, and this goes on and on and on again, generating substantial amount of great yield at this particular process right here. So this is where we have concluded with our reaction mechanism of this particular reaction, where we've used our palladium 2 double, we've used our other base, and we use our amine quite a high temperature, which is really fun to actually keep that in mind. So this then leads us to our final step, which is what are the alternative bases and what are the alternative ligands that are out there to enhance the yield and also improve this particular Buchwald Hartwig reaction process, where our goal is to be able to form a specific type of carbon heteroatom bond, either in the form of an aromatic ring with amine or possibly amides, which we're going to look at in our next videos. So this is where, in this case, other alternatives to this particular base or other alternative to our specific ligands comes into play, where on one side we need to first look at the base alternative, where we have our sodium tert-butyl oxide. We have another alternative, which is our sodium methyl oxide, and another one here is our lithium nitrogen or amine, which has this particular ligands. Probably is a negative charge for sure, so it's really interesting to see how this is really a strong base that will be easily deprotonating any form of nitrogen or amine that is in the complex. And finally here we have our potassium carbonate, that is also a good base, that is a great alternative for this particular type of reaction. And on the other side we have ligands that actually have a generic setup, which has a lot of Buchwald groups, where all these Buchwald groups are highly enhanced by the aromatic rings that are present. And this comes into play where we look at some coordinating regions around the palladium. Like for example, we have this particular form here where we have nitrogen with dimethyl coordinate region with our palladium. Another option will be a specific phosphorus form here, and another attached region to our palladium will be the same as the previous type of ligand. And looking at this ligand right here, we have another coordinate region where we have a palladium with a particular region acetyl, and we have phosphorus present with our tert-butyl regions. And finally here, this ligand here, and this is quite interesting to see how these ligands alternatives actually enhances the specificity of our specific product, and also the base actually speeds up the formation of our final intermediate that leads to the formation of our product. So thanks for following me through this particular video. I hope you found this particular reaction really fascinating, being able to look at the end game and also the reaction example, which is what we had. We looked at the reaction mechanism of the Buchwald-Hartwig reaction, and finally the base ligand alternatives that are out there to enhance this particular formation of our aromatic or our carbon heteroatom bond products. So thanks for following me through this. Really appreciate it. Hit the comment down below. Let me hear your thought about this. By that way, I can talk to you all soon. Stay smart as always and believe in yourselves.